So then we'll start. Okay, fine. So today we will look at velocity and acceleration. Velocity and acceleration. So if we have a function, let's call it phi of g of t comma t, then the total derivative of this particular function is given by dphi by dt is equal to del phi by del t, keeping g fixed, plus del phi by del g times dg by dt. So this is the chain rule, right? So we will need this chain rule when we derive the expressions for the velocity and acceleration. So this, suppose if you had a vector valued function which was a function of g which is also vector valued, then in that particular case I will get, so suppose if phi I, the component if I wanted, then I will get d phi I by dt is equal to del phi I by del t, keeping g fixed, plus del phi I by del gj now, and times dgj by dt. Okay, so we can easily extend. So this is for a scalar valued function, and this is now for a vector valued function. So you can easily extend it, and so here the vector valued function is a function of a vector g. So we can easily extend this chain rule to this vector valued function also. So here today we will talk about a new concept which is known as the material derivative. So many times we will have to use this chain rule, because we will see, for example, that some variable, let us call it density or temperature or something like that, that will be a function of the spatial position and time. Okay. Now this spatial position is itself a function of capital X comma t, correct? And so what will happen is that the we will be exactly in this particular kind of a situation here, because now this x is chi of x comma t, and so it depends. So this variable will depend explicitly on the time and also implicitly on the time through this particular relation here, right? So we will be exactly encountering this particular situation where some function which is a function of the spatial position and the time, then we will need to use the chain rule in this particular manner. Okay, so this is how we will use this particular result here. Fine. So now let us define what we mean by a material derivative. So this concept of a material derivative is not a very trivial concept, let me say. So we have to try and understand this very carefully. So suppose if I give a material field, so given a material field, so that is phi of x comma t, let us say, the particle or material derivative, denoted by dphi by dt is defined as d phi by dt is equal to del phi by del t, keeping capital X fixed. Okay. So this particle derivative is just another name for the material derivative. Okay. So that these are just two different names for the same thing. Okay. So this so here basically what we are doing is that we are holding x fixed and then we are taking the partial derivative with respect to time. So if you are given a material field, then actually the definition of the material derivative is fairly straightforward here. Fine. Now we will use this concept of a material derivative in order to define the velocity and the acceleration. Yes, so we'll define now. So in the Lagrangian setting, Lagrangian approach, the velocity v tilde of x comma t is equal to d chi by dt. Okay, and this is just del chi by del t, keeping capital X fixed. Okay. So basically, see what we are doing is that suppose this is your reference configuration. So this is your V naught, and capital X is the position vector of some particle. Then it will evolve, right? So you now have, this is your deformed configuration. So as this particle, so suppose this is the trajectory of this particular particle, then we are simply taking the derivative of the chi mapping with respect to time, keeping capital X fixed. Okay, so suppose if it were some other particle, then we are tracking this trajectory here and then again taking the derivative of this position vector here, or the function that defines the position vector with respect to time. So that is the definition of the velocity in the Lagrangian approach. Then similarly, you will get that a tilde of x comma t is equal to dv tilde by dt, which is equal to del v tilde by del t, keeping capital X fixed, which is also equal to del square chi by del t square, keeping capital X fixed. Okay, so now just a word about the notation here. So the if you see this notation, I am putting a tilde above the symbol v. So even here also I am putting a tilde above that. So the tilde below the symbol, that just indicates that it is a vector. So that is our usual convention, that we denote vectors by a tilde below the symbol. But this tilde above that, that is basically used to say that this variable is a Lagrangian variable. Okay, so in terms of capital X and t. So if we are using the Lagrangian version of the velocity or acceleration, I will put a tilde above that to indicate that it is a Lagrangian variable. If it is an Eulerian variable, so that means if it is a defined in terms of small x comma t, then I will not put the tilde above that particular variable. Fine. So now, so this is the definition of the velocity and the acceleration in the Lagrangian framework. Now let us define the velocity and the acceleration in the Eulerian framework now. So let us do that. So, so in the Eulerian description now, Eulerian description. So I will define the velocity v of x comma t as equal to v tilde of x comma t, which is equal to v tilde of chi inverse of x comma t comma t. So if you recall, just like we had x is equal to chi of x comma t, right? And so the inverse mapping will be given by capital X is equal to chi inverse of small x comma t. Right? So all I am doing is that I am substituting for capital X in terms of small x. So now you will see that this whole thing is a function of small x comma t, and now this function, right, whatever is this new function in terms of x comma t, I am calling that as the Eulerian description now of the velocity. Right? So this is, we'll call this as the v of x comma t here. Right. Then what about the acceleration now? So for the acceleration, so yeah, but before going to the acceleration, let me just illustrate this point using an example. So suppose if x is equal to capital X times 1 plus t square, y is equal to y times 1 plus t, and z is equal to 0, then you will get that Vx tilde is equal to, so basically take the partial derivative of this with keeping capital X fixed, right? So that will be 2 times xt. Then similarly your Vy tilde is equal to y, and Vz will just take it as 0. So now in order to get the Eulerian picture here, all you do is you substitute this capital X in terms of small x. So this will be equal to, so if I substitute now, so let me write x as equal to small x divided by 1 plus t square, and capital Y is equal to y divided by 1 plus t, then you will get that Vx will be equal to 2xt divided by 1 plus t square, and Vy will be equal to y divided by 1 plus t, right? And Vz will just take it to be 0. So you can see now that I am using this inverse relation to get capital X and capital Y in terms of x and y, and then I am just substituting it in this Lagrangian description of the velocity to now get the Eulerian description of the velocity, right? And so you will see that the way V tilde depends on capital X is different than the way Vx depends on small x, right? And so that is why these are different functions, okay? So Vx tilde is a different function of capital X than Vx as a function of small x, okay? And so finally, see, the velocity is the same, okay? So because of this particular statement, so we are not saying that the velocity is different. So these are not two different velocity vectors. Finally, the velocity vector is just a velocity vector, right? Whatever is the velocity vector here. It's just that in one case we are describing the velocity vector in terms of capital X, and in the other case we are describing it in terms of small x, okay? So only the functional form of the velocity, one is in terms of capital X, the other is in terms of small x. That functional dependence is changing, but the value of the velocity for a given capital X or the corresponding small x, that value is finally the same, correct? So that is, as I said, that is illustrated by this statement here, that finally the velocity vector is just, there is only one velocity vector, only the descriptions are different, or the functional dependence of V tilde on capital X is different than the functional dependence of V on small x. And so that is the reason that we are introducing this tilde to show that this is a different function than this particular function. So we have to be careful about this aspect as we go along here. Fine. So now we will define the acceleration now using the definition of the velocity here. So again, in the Lagrangian description, the acceleration can be defined quite easily, right? So that I think I have already defined. So in the Lagrangian approach, we have already seen, right, that the A tilde is equal to just del V tilde by del t, keeping capital X fixed. Now, suppose if I want to find out what is the Eulerian description of the velocity. See, why do we need an Eulerian description of velocity? So typically, if you see in problems in fluid mechanics or something, right? Typically, as I have already given you this example, we are studying flow in a channel or something like that. So we do not know, right? The water is coming in from some overhead tank. We typically do not know what the capital X is, right? And so, but we know what the small x is, right? Because we are sort of monitoring the flow in some channel or something like that. And then, when I want a expression for the acceleration, I would like it to be in terms of the spatial position, not in terms of the capital X, because this capital X I don't even know where the fluid particles are coming from, right? So in that sense, I would like an Eulerian version of this acceleration. So let us try to derive that. So this A of x comma t is equal to A tilde of x comma t, and this is equal to del V tilde by del t, keeping capital X fixed. So I'll apply the chain rule now and get an expression for the acceleration in terms of small x. So let us do that. So this here is equal to del v of chi of x comma t by del t, keeping capital X fixed. Correct. So all I have done is that instead of v tilde, I am now using the other function, that is v of x comma t, but x comma t that is actually a function of chi of x comma t. Right? Because we know that we know here that x is equal to chi of x comma t. Right? And so now we will apply the chain rule on this. So this is equal to del v by del t, keeping x fixed. Okay. So we are now we are using that chain rule, right? That at the beginning of today's class I indicated that. So first you take the partial of del v with del t, keeping g fixed, plus del v by del g times dg by dt, right? So exactly the same procedure. So this is exactly analogous to your g of t, right? Because it's a vector function, because the capital X is fixed, correct? That does not change with time, because that is just the position of the particle in the reference configuration. So, as I said, that this is exactly analogous to this particular situation here, and so I can apply the chain rule for this one here. So this is plus del v by del x1 times del chi1 by del t, keeping capital X fixed, plus del v by del x2 times del chi2 by del t, keeping capital X fixed, plus del v by del x3 times del chi3 by del t, keeping capital X fixed. Okay. So let us write this in initial notation, and then what we will get. So from here now, I'm just writing it here. So this is equal to del v by del t, keeping small x fixed, plus del v by del xj times del chi j by del t. So I'm just writing this in initial notation. So this is with the j is a dummy index with the summation convention, and so this is equal to del v by del t, keeping x fixed, plus del v times v, because this del chi by del t is nothing but vj, correct? And so this del v by del xj is nothing but, so in component form this would be del vi by del xj, and so this matrix we are just multiplying it by v, and then we get the Eulerian description of the acceleration, right? So this is the formula. So maybe I'll just erase this so that it doesn't confuse us, and so this is the acceleration formula. So this is del v by del t, keeping small x fixed, plus del v by del v times v. Fine. So let us try to understand this particular expression here. So suppose if you had a flow like this, right? And now imagine that it is what is called as a steady flow. So steady flow. So steady flow. So what that means is that your del v by del t, so there is no tilde here, sorry, the del v by del t at a fixed x is equal to 0. So this is what is called as a steady flow. So that means if you look at the velocity at this particular point, so suppose if the position vector of this particular point is x, and then now the velocity at this particular point, suppose if I call it as vx comma t, then this velocity is a function only of this small x. It is not a function of t, because del v by del t at a given x is equal to 0. Okay. So so the velocity. So if you look at this particular point, then it has some velocity, right? And then now suppose if I look away and then again look at it, the velocity is still the same, because it is not a function of time, right? It is not changing with time. So so what we have is that this part of the acceleration is 0, but the acceleration, right, is still not 0 because you have this additional term del v times v. So let us try to understand that. So what is happening here is that actually, so if you look at it at this instant of time, then there is some velocity to this particle. But if you look at now some other particle, right, that is going to come and occupy this particular position. And so this will be some other x prime or whatever you want to call it. So the particle which was occupying this position vector x prime is now coming and occupying this particular position, and the particle that is occupying this particular position is going to go to some new position, correct? And so the velocity is changing. So if you track this particular particle, its velocity is changing as it moves to a different position at a different time, and so this term will capture that particular effect. Okay, so even though at a given x the velocity is not changing, but as this particle travels, its velocity is changing, right? And so this nonlinear term captures the effect of that particular acceleration. So you have to be careful in computing the acceleration, that just because the flow is steady, the acceleration does not become 0, right? So only this term goes to 0, but you can have a contribution due to this particular term here. Fine. So okay, we can extend now these definitions to get the Eulerian material derivatives for different types of fields here. So suppose if I now take a scalar valued field now, so then how do I compute the material derivative in the Eulerian setting? So let us look at that. So suppose now for a scalar valued field, so if v of x comma t is a scalar valued field, okay, then its material derivative is d phi by dt is equal to del phi by del t, keeping x fixed, plus del phi by del xi times del chi I by del t, keeping capital X fixed. And so this is equal to del phi by del t, keeping x fixed, small x fixed, plus v dot del phi. So this is the way we will write this whole thing here. So one thing to note here is that many times, especially the books on fluid mechanics, they will write this term here as v dot del v. Okay. So now this is a very weird way of writing this particular term here. So you have to think of this as like an operator, v dot del operator acting on v. Okay. So it is sort of correct, but the proper tensorial way of writing it, the nonlinear term of the acceleration, is whatever is shown here, right? So basically you are writing it as a second order tensor. So this is the velocity gradient tensor, so which will define shortly. So this is the second order tensor, the velocity gradient tensor, multiplying a vector to give the nonlinear term of the acceleration vector. Okay, so this is one should not actually, ideally speaking, one should not write it in this particular way, because this is very weird way of writing this particular thing. But in this particular case, this is okay, because here I am putting the brackets not around the del but around the del phi. So here for the scalar variable, it's a vector, v is a vector, del phi is a vector, and just you are taking simply the dot product between two vectors. So here, as I said, that the parenthesis is around del phi. So here the parenthesis is around the del, and so you have to think of this as an operator acting on this particular thing here. Fine. So we will use this particular notation. So we will not use this notation which the fluid mechanics community typically uses here. So just to give an example here, so suppose if you had a, just to give an example of this particular term, so this will be del V1 by del X1, del V1 by del X2, del V2 by del X1, del V2 by del X2. That is multiplying V1 and V2. Okay, and then so this will give del V1 by del X1 times V1 plus del V1 by del X2 times V2. Okay, so this will be the term for the A1. Okay, and then for the A2, that will be del V2 by del X1 times V1 plus del V2 by del X2 times V2. So this is, so I am talking only of this term. In addition, of course, this term will also be there, but I am not just showing that particular term here. I am just showing the nonlinear term. So you can see that it can also be written like the V dot del, whatever I said, right? V dot del times V, because you can think of this as V dot del is V1 del by del X1 plus V2 del by del X2. So this operator acting on V1 because for the first component, so that is acting on this V1 here. And then similarly, V dot del is V1 del by del X1 acting on V2, correct? Because for the second component, and then similarly for the other term. But as I said that this particular thing we will not use, we'll just use this proper tensorial notation of a velocity gradient multiplying the velocity vector. Fine. Then, if I consider x as a spatial field, then the material derivative of x itself can be said to be the velocity itself. Okay, so considering x as a spatial field, so considering small x as a spatial field, right? As a spatial field. See, because we can consider it as a spatial field because generally we are writing a spatial field as some function of x comma t, right? So here it is a function, so x is a function of x itself, right? But not of time explicitly. So in that sense we can consider it as a spatial field here. And if you take the material derivative of that, then we get that dx by dt is equal to v. So this is since del v by del t, del x by del t, keeping small x fixed is equal to 0 because x is fixed, right? When you are taking this partial derivative with respect to time keeping x fixed, so this derivative will be 0 and your del x will be equal to the identity tensor, and that is simply multiplying the velocity vector, right? So del x times v will be equal to v itself, and so that is why v can be written as dx by dt. So here actually I am using the formula that if w of x comma t is a vector valued function, vector valued variable, then dw by dt is equal to del w by del t, keeping small x fixed, plus del w times v. Okay. So actually I am using this particular result here. So maybe I should have mentioned this result before going to this, but please note this result. So this is the derivation of this is exactly analogous to the derivation for the velocity vector, right? How we found the material derivative of the velocity vector. So same similar derivation here. So this is the result that you will get, and then I am simply substituting w is equal to x, and then you will get del x by del t at x is equal to 0, and del x is identity, and then multiplied by v, so you will get v is equal to dx by dt here. Fine. So now let us move on. So we will now define this term, this del v, which occurs, let me see where is, okay, the del v I think I erased, but the term del v will occur very often. So we will give it a new symbol and call it as a velocity gradient. Okay, so let us define that. Yes, so let us give the names for this one. So velocity gradient now, velocity gradient. Velocity gradient. So L is equal to del of v. Right? And so I can write the acceleration which we have just derived, right? Is del v by del t plus del v times v. We can also write this as del v by del t plus L times v, because we have now defined this as L. Okay. Fine. So we will now derive certain relations which are going to be useful in subsequent derivations. So we will derive now df by dt is equal to L times f. So L is this velocity gradient now that I have introduced. Then d of f inverse by dt is equal to minus f inverse times L, and 1 by j times dj by dt is equal to trace of L, which is equal to del dot v. Where this j is nothing but your determinant of f. So we'll derive these relations here. So okay, so first let us derive this particular relation. Df by dt is Lf. So this is del. So going back to the definition of the material derivative, del f ij by del t, keeping capital X fixed, is equal to del by del t of del chi I by del xj, keeping capital X fixed. Right? So this is just the so I have just used the component form of the deformation gradient and then used the definition of the material derivative to write it in this particular way. Now this t and capital X, these are independent variables, and so I can interchange the order of differentiation, and so what I will get is I will get the del v tilde I by del xj. That is because see, the del chi I by del t, after I interchange the order of differentiation, del chi I by del t, keeping capital X fixed, is your vi tilde. That is the Lagrangian description of the velocity vector. And now I can apply the chain rule to this. So this is del vi by del xm times del chi m by del xj. And so del vi by del xm is nothing but lim, that is the velocity gradients components, im component, and then this is nothing but fmj. Right? So what we have shown is that del fij by del t, keeping capital X fixed, is lim times fmj. And so when you convert that to tensorial form, then df by dt is lf. Right. Then the second one is fairly easy, because you just simply use the fact that f times f inverse is equal to the identity tensor, and so df by dt times is this particular part here times f inverse df by dt times f inverse plus f times d f inverse by dt is equal to 0. The identity tensor is a fixed tensor, so the material derivative of that is just 0. And then f is invertible, as we know. I already used this assumption, and so I will get that d of f inverse with respect to time is equal to minus f inverse L, equal to minus f inverse F, because so here I have just simply substituted this as LF. Right? So df by dt is LF, so whatever, and then f times f inverse is identity tensor, and so you just take it to the right hand side and then you will get this particular expression here. Fine, then the last relation here, that is 1 by j dj by dt, is trace of L. So we go back now to the result which dealt with the derivative with respect to time of the determinant of a tensor valued function. So there we saw that so dj by dt is equal to cofactor of f multiplied by df by dt. Right? So this result we have already seen. So maybe I may have used the symbol t in that case. So we saw this result when we were discussing differentiation of tensors. At that time we saw this result. If you want to derive this in indicial notation, that is also another option. So for example, you can write del j by del t, right, having capital X big, is equal to del j by del f ij times del f ij by del t, right, keeping capital X fixed. And so this is nothing but the cofactor of f. So this we have already seen, and then that matrix inner product with df by dt, because this is nothing but the material derivative of the deformation gradient. Right, after this then it's just a matter of again substituting LF. So this is equal to cofactor f times LF, and this I can write as cofactor f times f transpose times L, and the cofactor f times f transpose is nothing but determinant of f times the identity tensor, right? So this this term here is determinant of f is equal to determinant of f times the identity tensor times L. Correct? So this will give me the trace of L, because matrix inner product of the identity tensor with L is nothing but the trace of L itself, and so this is nothing but J itself. So this is equal to J times trace of L, and since L is equal to del of V, so you get that trace of L is equal to del dot V. Correct? And so you can also write it as J times del dot V. Right? So that is the third result. So all these results actually are very, very important, and you will see that they will be used in lots of derivations. So you should know these results quite thoroughly. Fine. Then we'll move on. So now we will split the velocity gradient into a symmetric part and an anti-symmetric part. Okay, so we have already seen that a tensor, any tensor, can be decomposed uniquely into a symmetric part and an anti-symmetric part. So let us do that. So here L is, I will call it as D plus W tilde. So this tilde I am putting because sometimes it can clash with W, which I am using for some other purposes also, and so on, like Q dot Q transpose many times we will denote by W. So just to avoid a clash of notations, I am just putting a tilde above the W here. So this D is nothing but the symmetric part of L. So this is L plus L transpose, and W tilde is half of L minus L transpose, right? And so yes. So okay, so this we know that this decomposition is unique. So this D, which is the symmetric part, is known as the rate of deformation tensor. Okay, deformation, and this is nothing but the vorticity tensor. Vorticity tensor. So this there is a a slight difference in the terminology used by the continuum mechanics people and by the fluid mechanics people here. So this rate of deformation is the terminology that is used by the continuum mechanics community, while the fluid mechanics community calls it as a rate of strain. Okay, so or strain rate, whatever, or strain rate. Actually, maybe this terminology may not be so appropriate, because actually D is not the rate of any strain. So later on we will show that it is neither the rate of the Lagrangian strain nor the rate of the Eulerian strain or any strain for that matter, but it has the same units as a rate of strain. Okay, so that is the only thing. But actually, so that is the reason the rate of deformation is a more appropriate terminology rather than rate of strain. And so why rate of deformation? So that actually is given in the book. I mean the physical interpretation. So we will not go into that physical interpretation here. As I said, you take a look at the book, either the first volume or the second volume here. Fine. Now, just like we gave a characterization of rigid motion in terms of the mapping chi, right? We have seen that chi is equal to q of t times x plus c of t. So in the same way, we can give a characterization of rigid motion in terms of the velocity gradient or the rate of deformation tensor. And so now let us look at that second characterization now. So in order to do that, let us just recall what we mean by a rigid motion. So a rigid motion is a motion in which the distance between any 2 points remains the same, right, throughout its motion. So another way of expressing this is that the time derivative of the distance between any 2 points is 0, correct? Because the distance is not changing with time, so the time derivative of that distance is equal to 0. So so motion is rigid. A motion is rigid if del by del t of chi of x1 comma t minus chi of x2 comma t is equal to 0. Okay, so for all capital X1, capital X2, and for all t also, correct? So this is how we can all define. So in the previous characterization, we had just said that the distance between any 2 points, this chi of x1 comma t minus chi of x2 comma t is equal to x1 minus x2, right? The mod of x1 minus x2. So that was another way of saying it, but now this is an alternative way of saying the same thing here. So now let us give a characterization of the second characterization of this rigid motion in terms of the either the velocity gradient or the rate of deformation tensor here. So this relation I will call as star, okay, but I am going to erase this particular relation, but just recall that this is going to be called as a star in the theorem that I am going to write here. So yes, so so this is the theorem. So theorem. This is characterization of rigid motion. TFAE as usual stands for the following are equivalent. One is that chi is rigid. So then that means this star holds. Okay, so star holds. And the two is that V at each t, V of x t is W of t times x plus C of t. Or this can also be expressed in an alternative form. So you can also express it or V at x1 comma t is equal to V at x2 comma t plus W of t times x1 minus x2. So this is just an alternative form of the same statement. Just if you evaluate this at x1 and x2 and subtract, you will get this. And if you fix x2, right, and then you will get back this particular statement here, right? So you can express it in either of these two ways. So I'm now going to erase this, but as I said, that star is that particular relation here. And then the third statement is that L of x comma t belongs to skew. Or alternatively, or d of x comma t is equal to 0. Okay, so now let us prove this particular theorem here. So proof of this. Yeah, so we will show that 1 implies 2 implies 3 implies 1. So this is what this is the sequence that we will follow here. Fine. Okay. So first let us show that 1 implies 2. Okay. So 1 implies 2. So that means that star, whatever I said, that del by del t of the distance between any 2 points is equal to 0. So that holds, right? And then now we want to show that V has this particular representation, whatever I have put here. So, so if I now write that del by del t of, so I will just rewrite that del by del t of chi of x1 comma t minus chi of x2 comma t dot of chi of x1 comma t minus chi of x2 comma t is equal to 0. Correct? So this is the derivative, time derivative of this is equal to 0. So if you now use the usual product rule and so on and so forth, then what you will get is that x1 minus x2 dot of v of x1 comma t minus v at x2 comma t is equal to 0, right, for all x1, x2 belonging to v. Yes. Okay, so now let us differentiate this with respect to x1. So differentiate with respect to x1 now. Differentiate with respect to x1. And you can use the usual initial notation to differentiate this with respect to x1. Then what we will get is that v at x1 comma t minus v at x2 comma t plus del v at x1 comma t transpose. So actually this is, or let me just put it around this so that there is no confusion. It is this transpose of this del v plus times x1 minus x2 is equal to 0. So now you differentiate this, yet another time with respect to x2. Now differentiate with respect to x2 now. Okay, then what you will get is the following. So you will get now that del v of x2 comma t plus del v of x1 comma t, the whole transpose is equal to 0 for all x1, x2 belonging to. And just similar to the proof of the first characterization, right? We set capital X1 equal to capital X2 in that case. Here, in a very analogous fashion, we will set x2, small x2 to be x1. Okay, so take x2 to be x1. So you will get, so set x2, so let now x2 be equal to x1. Okay, so what you will get is that you will get that del v at x1 comma t transpose is equal to minus del v at x1 comma t, and so this shows that del v is a skew symmetric tensor at every point, right? This is valid for all x1, right? So this is what for all x1 and for all t. So this means that del v belongs to skew. Right? So this is all what we have shown. Okay, and now if you now use, so let us go back now to this particular statement here. So let us call this as 1. So then now from 1, so from 1, what you will get is that del v of x2 comma t. So now we have shown that del v is a skew symmetric tensor. So the transpose is equal to minus of del v of x1. So if I write this, I will get that del v of x1 comma t. So this is valid for all x1, x2, right, belonging to v. And so this shows that del v is independent of x. So this implies that del v is equal to del v of t itself. It doesn't depend on x. Or let me just rewrite this, is equal to w of t, which belongs to skew. Let us put it in this particular way. And then just integrate this particular relation. Then you will get that, so now from this particular statement, we will get that v is equal to w of t times x plus c of t. So this c of t is like a integration constant. When we integrate this particular relation, this c of t is just like an integration constant. Or if you find the gradient of this, you will see that you will get back w of t, right? And fine. So this completes the proof for 2 implies 3. So now, sorry, this completes the proof of 1 implies 2. Now let us show that 2 implies 3. Okay, so fine. So okay, so now let us show that 2 implies 3. Okay, so here, if I just simply take the velocity gradient here, so since v is now w of t plus x plus c of t, and now this will imply that del v is equal to w of t, which belongs to skew, and this will imply that L, right, is equal to w of t, and d will be equal to L plus L transpose divided by 2 will be equal to 0. So that so this part is a trivial part, and now again the 3 implies 1 is a non-trivial proof. So let us try to show that 3 implies 2. So now we are given that L is w of t or d is equal to 0, and we want to show that star relation, that means the distance between any 2 points is not changing. We want to show that particular thing, that particular result here. So let us now try to show that 3 implies 1. Yeah. Fine, then so choose some fixed x1 and x2. So choose x1, x2 belonging to V, and let x of s be equal to x2 plus s times x1 minus x2. So this is actually the parametric equation of a straight line. Okay, so this is just a straight line. Parametric equation of a straight line with s as a parameter. So if s is equal to 0, right, you will get x2. Okay, so let me just draw this. So this is your x2, this is your x1, and this is your s equal to 0, right? So at s equal to 0, you get x equal to x2, and then if s is equal to 1, then you will get x1, right? So this is s equal to 1. So this is just a parametric equation of a straight line that joins x1 and x2 with s is equal to 0 at x equal to x2 and s is equal to 1 at x equal to x1. Yes, so now if I write the velocity in terms of this parametric representation, then let us see what we get. Yes, so v at x1 comma t minus v at x2 comma t is equal to integral from x2 to x1 of dv. So we can write it in this particular way, and this is equal to integral from 0 to 1 of del v times del x by del s times dx. So here I am just using the chain rule. So I am writing this as del v by del x times del chi I by del s times dx. Okay, so this I am just using the chain rule, and this is nothing but the velocity gradient here. So this is the limits are from 0 to 1 because we have already indicated that the limits for s are from 0 to 1 here. Fine. Then yes, so this is equal to now. So if I use this parametric equation, you will see that del x by del s is nothing but x1 minus x2. So I can substitute that here. I will get that this is 0 to 1 of del v times x1 minus x2 times ds. Now take the dot product of this with respect to x1 minus x2, and then what we will get is the following. So if I take the dot product with respect to x1 minus x2 dot of v of x1 comma t minus v at x2 comma t, so that is equal to 0 to 1 of x1 minus x2 dot del v times x1 minus x2 times ds. And now this we know that that is a skew symmetric tensor, right? This del v is w of t belonging to skew, and then we have seen that u comma wu is equal to 0, correct, for all u. Right? If w belongs to skew, then using the definition of the transpose of w, we have already shown this particular relation here. So this is equal to 0. Yeah, just one point here is that we can take this x1 minus x2 inside the integral here. That is because the x1 minus x2 is not dependent on s, and so that is the reason that we can take it inside the integral sign in this particular case here. And then after that point, we can just use the fact that u comma wu is equal to 0 here. Yes, so that is what I get. Fine. So So that shows now that so this was exactly our statement, that this was exactly star, right? That x1 minus x2 dot v at x1 comma t minus v at x2 comma t is equal to 0. This was exactly the first statement here. So now we have shown that 3 implies 1, okay, so which is what we had set out to prove. So that completes the proof of this particular theorem here. So actually we can give a simple proof if we assume that the velocity field is twice differentiable. Then we can give a simpler proof to show that del v is a constant tensor when d is equal to 0. So let us try to give this simpler proof also. Yes, so so assuming v of x comma t to be twice differentiable, simpler proof, so suppose simpler proof can be given for showing that del v is constant with respect to x, when d is equal to 0, and d so let us show this simpler proof. So since d is equal to 0, so since d is equal to 0, we can, so I write it in initial notation. Del vi by del xj is minus del vj by del xi. So this is the dij component of so this is the dij component. And now if I differentiate this with respect to I, then I will get the following thing. Not differentiate this with respect to some other index, k, let us call it. So del square vi by del xk, let us call it xj. And this I can write as equal to, so use this particular result here, so minus del square vj by del xk del xi. So what I have done is that I write this particular thing, I can write as del by del xk of del vi by del xj, correct? And now del vi by del xj is minus of del vj by del xi. So I can write it in this particular way. Now I can interchange the order of differentiation here. So I will get minus del square vj by del xi del xk. And then again use this particular result here to interchange these indices here. So I will get that this is del square of vk by del xi del xj. Then again interchange the order of differentiation. So I will get that this is del square vk by del xj del xi. And then again use this particular result here to interchange the indices. So this is the minus of del square vi by del xj del xk, and again interchange the order of differentiation. So this is again minus of del square vi by del xj del xk del xj. So what we have shown is that del square vi by del xk del xj is minus of del square vi by del xk del xj. So basically this object is equal to 0. So this implies, so what we get, so this implies that del square vi by del xk del xj is equal to 0. So basically what we have shown is that the velocity gradient is independent of x itself. Right? So what we have shown is that the del Vi by del xj is independent of x. Right? So that is what we have shown, independent of x. And then from this point onwards, you just integrate that. So then you will get, so this will imply that V is equal to W of t times x plus C of t. Right? So because then after this point, we can just simply differentiate that to, integrate that to get that V is equal to this W of t times x of t. So here actually, so the what is the difference between these two proofs here? So the difference between these two proofs is that in the first proof, I assume that V is only once differentiable. See, because we only use del V, we did not use a gradient of the velocity gradient. Whereas in the second proof, we used the fact that V is twice differentiable. So that is the main difference between these two proofs. Typically, mathematicians like to make minimal number of assumptions in their proofs, and so a mathematician would prefer the first proof, but for an engineer, I think the second proof is also fine, because typically we will take, we will many times we'll just assume infinite differentiability of all the fields and so on and so forth. So it's just that what are the assumptions that you make. So the second proof assumes that it is twice differentiable, whereas the first one assumes that it is only differentiable. So that is the only difference in these two proofs here. Fine. Now, how do we connect between the first characterization and of rigid motion and the second characterization of rigid motion? So we have seen that in the first characterization, we have seen that chi of x comma t is equal to q of t times x plus c of t. So if you now differentiate that with respect to time and write it in terms of small x, you will see that this w of t is nothing but q dot q transpose. Okay, so this so if you connect it from here, so basically differentiate this with respect to time, keeping capital X fixed, that will give you the velocity, and then you substitute for capital X in terms of small x. So finally what you will get is that you will get that this w of t is equal to q dot q transpose, which is a skew symmetric tensor. So this is the way you can connect between the first characterization of rigid motion and the second characterization of rigid motion here. So you can write, so because this is a skew symmetric tensor, we can write it in terms of the axial vector. So let us write that, and that axial vector is nothing but the angular velocity vector. So let us just write, so suppose if I write now v at x1 comma t is equal to v at x2 comma t plus w of t times x1 minus x2. Right? And write it in this way, and now because w is a skew symmetric tensor, I can write it in terms of its axial vector. So this is v of x2 comma t plus omega of t cross of x1 minus x2. So this omega is nothing but the axial vector of this w of t, which is also the axial vector of this q dot q transpose. So actually, I mean, this sort of gives us a very systematic way of finding out what the angular velocity vector is. So this omega of t is an angular velocity vector, and so as I said, that this characterization gives us a very systematic way of finding out the angular velocity vector. Now you may say, okay, that may be physically obvious. So it is physically obvious if the motion is just within one plane. So suppose if you have a disk that is just rotating in one plane, then it is physically obvious that your angular velocity is perpendicular to the plane of motion of the disk. But you imagine a spinning top, for example, where the top is spinning about its own axis, and that axis is also spinning about the vertical axis. So that axis is also spinning, and then the top is spinning about its own axis. And so in those kind of situations where a very complicated 3D motion is involved, then finding the angular velocity vector may not be such a trivial task. So the systematic way of finding the angular velocity vector would be that you first find out what this q of t is, right? From the motion, you find out what the q of t is, then you construct this particular object, the q transpose, which is going to be a skew symmetric tensor, and then take the axial vector of that skew symmetric tensor. That will give you the angular velocity vector. So as I said, that in sort of complicated motions, it would be better to find the motion and then figure out what the angular velocity vector is from that particular thing here. Okay, so now I have already mentioned that the rate of strain tensor, or the rate of deformation more precisely, is actually not the rate of any strain. So let us try to show that now. So if I now write, so let us take the rate of the Lagrangian strain tensor. So this is half of f transpose f minus identity. So if I take now d by dt, let us find that. So d by dt is half of df transpose by dt times f plus f transpose d f by dt. And we have already seen that df by dt is equal to L times f. And so if you substitute that in this particular expression, then what you will get is that you will get half of f transpose times L plus L transpose times f. And so this is equal to f transpose times d times f. So you can see that this d is not equal to d by dt. So because these additional factors f transpose and f are sitting on either side of d, and so you can see that it is not equal to this the rate of this Lagrangian measure of strain here. Similarly, actually you can also show that it is not equal to the rate of the Eulerian strain measure, which is that Almanzi strain measure also. So you can show that d e bar by dt is equal to d minus L transpose e bar minus e bar times L. Okay, so this you can show by using this particular relation. So E bar is F inverse transpose times E times F inverse. And so if you take the material derivative of dE bar by dt, and then we have already derived what dE by dt is, and from the second relation, right, we have dF by dt, and we had also derived one relation for dF inverse by dt. So if you use all those relations in this particular relation, then you will get this particular result here. So again, you can see that because there are these additional terms now, d is not equal to the rate of the Eulerian strain tensor also. So basically calling d as a rate of strain is a misnomer. A misnomer just means that you have given it a wrong name, but its use in the constitutive relation for a fluid, for a Newtonian fluid, that is correct. So mathematically there is no problem. It's just that the name is incorrect. I mean, basically we should not call it as a rate of strain, we should call it as a rate of deformation. So that is the more correct way of calling this particular thing. Fine, then what about the vorticity tensor? So this W tilde I have called as half of L minus L transpose. And so this quantity plays a key role in fluid mechanics. So if I now find the, so this is also equal to half of del V minus del V transpose. Right? So if you find, so this is a skew symmetric tensor, and if you find the axial vector of this, then that is related to the vorticity vector. So suppose if I now define the vorticity vector, so that is omega is equal to del cross B, for example, then this omega by 2 is the axial vector of W tilde. Okay. So if you take 2 times the vorticity tensor and find out the axial vector of that, then that is exactly the vorticity vector. And as you already know, the vorticity vector is a very physically very important quantity in fluid mechanics. So this one can easily show. Okay, so in the next class, I think I will give some examples of these various kinds of motion. So we will give the example of a pure extension, then rigid motion, which we will analyze in greater detail, and simple shear motion. Okay, so these, so far, I mean, all this analysis has been sort of theoretical analysis, in the sense that we have not actually shown how to compute the deformation gradient and rate of deformation gradient, the velocity gradient, velocities. We have not yet shown them for any particular example. So hopefully in the next class, those things will become clear.